Hi, my name is Zackary Lipton. I'm from University of California, San Diego, and currently also at Microsoft Research Labs in Redmond. So I guess in this crowd I could skip any kind of motivation for why we care about the topic in the first place, because previous speakers have done a good job. For policy reasons, because we're using machine learning in the real world. There's a lot of context in which people want to know how is the model working, or can I get some interpretation of its output. You might want to know, is it racist? You might want to know, is it working properly? In this talk, basically what I want to cover is I want to say, first of all, I think the thrust of this paper is to say that a lot of the conversation about interpretability is maybe well motivated but somewhat inconcrete. We want to get at precisely what is it, and is it one thing or is it many things? And if it's many things, then what are the desiderata that interpretability serves? And what notion of interpretability is appropriate in each context? I think that these kinds of clarifications are important to make to actually make progress, at least in the kind that we make in machine learning. If we want technical progress to offer an interpretation, we need a specification of what the goal is. As a starting point, I came to this sort of the claim as a young PhD student. People are saying deep learning gives good predictive accuracy, but it's not interpretable. And I say, usually people say, but a linear model is. So immediately I want to say, well, what is the property that the linear model has? And that's sort of the avenue by which I get to this. So if you look through different papers, you'll see many different models, whether they're sometimes it's linear models, sometimes it's decision tree-based methods or rule-based systems. But you see a sort of claim that's a form of a claim that a model is proposed. It's stated just categorically, like axiomatically, this model is understandable or intelligible or transparent. Usually this is supported maybe with just sort of an anecdotal example of some kind of visualization without an explanation of what precisely it's offering. And then there's a sort of skip forward to the technical details of the algorithm. The question is, what precisely is interpretability, and are they all talking about the same thing, or are they not? I guess from the way I'm setting it up, it's obvious that I don't think we're all talking about the same thing. I think a very clear example is that many papers say something like in a medical context, for example, people say, well, a doctor can tell you why he's recommending this treatment, but the model does not. So the human is interpretable. Other models say that deep learning, for example, would not be interpretable because we can't look inside the model and say precisely, exactly how does it arrive at its decision. But I also can't look in, the doctor himself is a black box. So there's sort of an obvious contradiction, and there's many contradictions. What we hope to do is resolve them. So to sort of just, the one thing that I think does bind all these different discussions of interpretability is that it's something other than predictive accuracy. So we could look at supervised learning, which is basically not the only paradigm for machine learning, but maybe the only one that is widely used in the real world at present. So usually we have some input, we have some desired output that we want to sort of recover a mapping or recognize some patterns. And the only thing that we require from the model in order to calculate our performance metric is this output. So we have an evaluation metric which sort of acts upon the predictions together with some ground truth and says, how good are we doing? Then a human comes along and says, in addition to this evaluation metric, that's not really enough to satisfy me. I also want some kind of interpretation. So if nothing else, we could say that the interpretation is something that comes out of the model besides the predictions and besides the accuracy that they achieve. So what's going on? Either the metric is correct, and all we care about is predictive accuracy, and people are just kind of irrational and they're crazy, or I think the sort of only other possibility is that the metric is not really enough. So anytime we're asking for an interpretation, is some context in which the metric, whether it's accuracy or area under the curve, does not fully describe our real-world desiderata. So what I'd like to do in sort of the first part of this talk is just go through what are some very classic examples in which that happens. I'll show that there are different ones, sort of disjoint set of scenarios in which our evaluation, our sort of quantitative evaluation in our real-world application of machine learning becomes sort of untethered. And then sort of in that context, discuss what are the different properties that people propose to confer interpretability and how do they relate to those desiderata. And we did this, in a paper, and you could check out the paper because 10 minutes is short, but try to do this in dialogue with the literature. So one thing that a lot of papers talk about, and this is probably the most inconcrete of all of them, is trust. They say, well, in order for people to trust the model, it has to be interpretable. Very often the conversation just ends there, and they go on and describe the technical details of the model. I think in some papers, if you look through, you can find a few different notions of trust. One is, does the model know it's uncertain? Can the model tell us when it's not sure? If it's not, if you train a model and you train it only on benign or malignant tumors, and then you show it a picture of a dog, it's going to tell you it's either a malign or a malignant tumor, and it might do that with high confidence. Another thing we might care about in terms of trust is, does the model make the same mistakes as humans? What mistakes it makes is something that's not necessarily captured by the accuracy, but it might matter in the sense of trust. If I'm going to defer control to the model, I want to know that I'm not taking a big risk. I'm not going to leave a model that's going to make mistakes that I would have caught. If the model's errors are strictly a subset of the errors that I would have made, then I might trust it because, hey, I would have screwed it up too. Another reason why our real problems become untethered from the machine learning formulations is that very often we don't really just care about these sort of strictly correlative predictions. We actually care about learning something about the environment, learning something about the mechanism that produces data, or capturing some kind of causal structure. A good example of this, Rich Caruana, and I'll sort of point to his paper or my paper, however you want to access it to understand this, points out a scenario where they try to predict the risk of death, the probability of death, given that someone is entered into the hospital. And presumably this is useful because if they're at higher risk of death, you would triage them into a higher level of care, send them to the intensive care unit. And so they train a model, and it shows that given that someone has pneumonia, if they also have asthma, they're at lower risk. The reason why they're at lower risk, though, is because they've historically been treated more aggressively. So if you train this kind of model, you're capturing a true correlation in the data, but it's just not useful. It's sort of misleading you if you're going to take an action where you're hoping, now you're intervening in the world, you care about causality. Should I downgrade the level of care of the asthma patients? No, that's sort of like intuitively ridiculous because we understand what's going on here. Another reason why we might care to sort of try to examine our models and not just trust accuracy is that we might have constructed sort of a very toy problem, and the real world might not obey the properties that our constructed problem exhibits. Like, the real world might be non-stationary, but our data is IID. So we might want to look and try to interpret the model to see, did it come up with a sort of plausible hypothesis that we expect to work in the real world, or did it depend on some weakness in the problem formulation? And yet another reason why we, I think, often care about an interpretation is that we set up the model as though the machine is going to make a decision. And so it's going to output, is this loan going to default or not, and that's going to make a decision. But very often what's happening is the model thinks it's giving an answer, but actually it's giving a feature. And the feature is to a decision maker who takes it into account as one among many different sources of information. So sometimes I think when we say we want an interpretation, it's simply that we want more information, because ultimately, and if that information helps us to make a better decision, then it's useful. If not, there's a researcher named Bean Kim who does some interesting work on interpretability, where she looks at precisely this notion of interpretability with a human study, where you have a clustering algorithm, and she generates something she calls an interpretation, but the validity of whether or not it's good is it's being used by a human to perform a task. And if the human performs the task better, then it was a good interpretation. So now I'd like to sort of just break down what are the different model properties that are proposed, that are claimed to confer interpretability. And I think these cleave nicely into two camps. On one side, I think there's transparency. And what I call transparency is different from sort of explanations. So transparency is sort of, can I look inside the model? Do I know how the model works? And explanations are, some kind of post hoc, like for example, what a human gives. I say I made this decision for some reason, but you don't know how the brain works. And even within transparency, I think we could break down into some very specific subtypes. One notion that you see is what I call simulatability, but another word for this might just be simplicity. And the idea here is, can a human take in the entire model? The model is interpretable in this sense. It's transparent in this sense if I, say, have a linear model with 10 features, and I could look through and say, the model did precisely this calculation, and this seems reasonable to me. Or decision tree might be interpretable if it were sufficiently small and I could step through. But of course, if the path were long enough from the root to leaf, or if the linear model had enough features, then there's no reason to say that like a linear model or a decision tree is intrinsically interpretable. If you have a model that has 10,000 features or complex basis functions, then this kind of all goes out the window. Another notion that I think is pretty common is what I call decomposability. So you say maybe you can't completely understand the entire model. Maybe I can't look over every single decision it possibly can make, but I can look at any given parameter and say, does this somehow accord with my intuition? I think this is what people most often mean when they talk about a linear model being interpretable. They mean I can look at the weights. And I say, what is the weight? The weight is how strongly the model, conditioned on everything else, upweights the probability, right, given a particular feature. And what I don't think people really often mean, but it's maybe a third notion to consider, is is the algorithm well understood? Like, do I understand how the algorithm works? For example, and this may be the biggest sense in which the linear model has something that the deep learning does not, is that we understand the optimization procedure for the linear model. We know that at least on the training data, the model is going to choose a unique global minima that minimizes a convex loss function among all the models in the family. And the neural network is, this is sort of, we have a non-convex error surface, and we train it by stochastic gradient descent, and we pray to God, and usually he's kind to us, but we don't know why. So I think now there's sort of another family of, this was originally an animation, and Batman actually scratches his chin and thinks very hard. But I think another family of things that are called interpretability are these post hoc explanations. These are explanations that don't really explain what the model is doing in a sort of, now I understand the full mapping, I understand the behavior, but maybe they give you some intuition. And I think these are things that we often use as researchers. So things like you say, well, what if I take a gradient step on the input to emphasize a particular node? I can look at the input and see how it changed and say, maybe this tells me what's going on in this node. Maybe it tells me what this node is sensitive to. Does that really mean something concrete mathematically? I don't know, probably not, maybe. One notion of post hoc interpretation might be a verbal explanation. You could even think of an image caption as sort of a verbal explanation of an object recognition system, since they are usually trained on the same features. So here, you can imagine that you train a language model. You might train an object recognition model, which is used to train a ConvNet, and then you might train a language decoder, which is able to generate a description of it. And this might give you a sense of what the model is sensitive to, what it sees, what it doesn't see, what blind spots it has. The danger, of course, of a verbal explanation is that you might get an answer that sort of seems plausible, but doesn't actually describe the behavior of the model. And we don't really have a concrete mathematical way of saying that these two are connected. I think humans do this all the time. Like you think of admissions officers at colleges, or even the law. In the law, we say we give you this sentence because of this very objective reason that's encoded in the law, but if you actually look statistically, a huge number of the death sentences that are given versus, say, life in prison are given because someone happens to be black or happens to be Latino in America. Or the sort of reverse thing happens in college admissions, where people say they accepted some student and not another because of leadership qualities. But this was sort of a code word for because they were Jewish or because they're Chinese now, or whatever is the overrepresented group. So I think we have to be very careful about a sort of a model that gives us a verbal explanation that people want to believe, but maybe not actually, may not actually faithfully describe the behavior of the model. I talked about before, saliency maps, sort of visualizations are a thing that give you a local explanation. You have a neural network. At a given point locally for a single example, you can take the derivative all the way through the entire model and say, if I move any one of my input features, how does it affect my output? This gives you intuition. It's useful. It guides research. People depend upon this to improve the models, but it doesn't really fully describe the mapping. And case-based explanations might be another kind of post hoc interpretation that people may or may not find useful. This is when you say, I think this patient looks like these other patients, and seeing which ones look similar from the perspective of the model. So in a neural network, this might be that if I take the representations that are learned and I calculate nearest neighbors, these are the in the representation space. This is what comes out. So anyway, I don't think I have much time. Maybe I'm out of time. So just some discussion points that maybe we could discuss over lunch or anything if you are interested are, one, I think we have to be very careful about making these categorical claims. To say linear models are strictly more interpretable than deep learning models sort of is a kind of unnuanced statement that is or isn't true depending on what kind of interpretability you're after. If you're after having more information, the deep learning model might be more interpretable because it gives you this rich learned representation that tells you a lot more about your data than a linear model does. But if what you care about is explaining the parameters, then maybe it does. I think we should just qualify all of our claims about interpretability, or else we're going to have a hard time making progress if no one knows what anyone is talking about. And I think some weaknesses of each kind of approach to generating interpretation is, on one hand, most of the ideas that fall under transparency are seem kind of overly restrictive. They, in order to create a model that is simulatable, you basically rule out any model that is powerful. In order to create a model that is decomposable, you might also rule out any model that is powerful enough to do anything interesting. On the other hand, post hoc interpretations could mislead. We could have a model that gives us, sort of placates us. We can have someone train a process to generate a verbal explanation that we want to hear but doesn't faithfully describe, might obscure some pernicious behavior in the model that we don't want to see. So that's all I have. If there's any questions, happy to take them now or later.
I think that we have 5 minutes for questions, and I would ask Federico if you could move your talk in the afternoon. Okay, so thanks. So,
Yes, just a full question, and maybe you don't know the answer at all. When I look at let's say the advertising or the editorials of Watson, and you go to the site, then they basically claim, for instance, for medical diagnosis, that the system comes up with explanations how they come with the diagnosis, so other diagnoses, etc. Could you place that in terms of what you have discussed?
Well, Watson is describes many pieces of software and maybe even many units within the IBM team, and I think they use the term Watson as an umbrella term, especially following Jeopardy, to describe anything AI related. It's rational. So it's hard to say at large what is Watson and what is the interpretability that it offers. I've seen some different presentations from some of the people on their team who are doing really interesting work, and so I think you have a mixture of things at play. I think I've seen some work where they definitely do have something of a sort of decision tree process that they probably do, because this is sort of how doctors sometimes represent decisions. They draw a flow chart of how you arrived at it. But I'd say to offer a really specific answer, I'd like to look at a specific implementation, because I'm sure they're doing many things. I'm sure they have linear models in part of what they call Watson. I'm sure they have deep neural networks. I'm sure they're giving people visualizations, and I'm sure they're showing people decision trees. So absent a more concrete example.
Okay, then maybe a very tiny extra question. Would you think it is interesting and important in that case to have a sort of contestability of the interpretation? So you have a system like that, you have doctors following that, using it. There's all this talk that what a particular doctor can calculate in her head will never match up with what Watson, whatever it is, can do. So it might be good support. But then I would like to have some sort of contestability built into it. So if as a doctor I look into the system, I'm going to use it, can I somehow say, and then tap into something else, which preferably is not from IBM, if you get my point. Which raises a lot of questions about my usability.
Yeah, I think it would be great to be able to define the interpretation in so concrete a way that you could contest it. I think that might be more difficult to do than to say. But especially, I work with medical data a lot, and the data could be really messy. You can have, I work on some data, for example, where we just got a new data set and we look and some patients are 1,000 pounds. And it turns out that are 700 pounds or something. But basically what happened was that for some subset of the patients, they made some like unit error. And so the kilograms got turned into pounds or something like that, or the other way around. But yeah, I think this kind of gets to one use that I don't describe enough in the paper of interpretability, which might actually be just the use in debugging, the spotting that something's wrong. Like as a doctor, like you want to contest in part to say, are you depending upon some erroneous information, or are you depending on something? Because medical data, you get diagnoses that are part of electronic health records that might not actually apply to the patient. This is largely for billing purposes. So you have a patient who comes in, and the patient looks like they might have MS. And so the doctor says, okay, well, if you might have multiple sclerosis, we need to send you for an MRI, or we need to send you for a spinal tap. So they send you, but they need to bill the insurance company. And to bill the insurance company, they need a diagnosis. But they don't have a diagnosis because you haven't been diagnosed yet, so they put down like the provisional diagnosis of what you're being tested for. And then when it comes back negative, this may or may not leave your chart. So yeah, I think there are definitely clear cases where being able to sort of push back on something, especially if the model is depending on faulty evidence, could be really useful. Thanks for the question.
I think you made a lot of great points on the limits of interpretability in linear models. I agree with everything you said.
Everything? I don't agree with everything.
I just want to add one point.
Yeah?
Because I really love linear models. And one thing that you haven't mentioned is that in some application domains, the linear model actually gives you a way to uncover latent structures. So I'm using machine learning in brain science, and in the brain, the forward model, actually, how the brain activity is spread into the sensors is linear. Actually, the inverse model is also linear. So what turns out, if you use linear models on brain data, they often help you find sources in the brain. Sorry, it's a very detailed comment. They uncover sources in the brain that tell you something about whatever condition you're investigating. So another function of linear models is uncovering latent structures, which I think makes them quite sexy in an application if you have a linear system.
Yeah. Well, I think the benefit of using a nonlinear model is if your data is nonlinear. If you're mapping from an image, say, to a classification, this is a very obviously nonlinear relationship. And if you train a linear model, it'll fail. If your data truly is linear, then there's all kinds of advantages to actually representing, modeling it with a linear model. So yeah, that makes a lot of sense. I think when you're in a more complicated domain where I think probably the majority of natural data sets are not linear, then the kinds of latent structure that you need probably aren't going to be recovered just by a linear projection. So, but